temperatures are tremendous in the furnace of a modern boiler. The heat is used to make steam for industrial and utility use, but some of this tremendous heat is wasted. One of the reasons heat is lost in the process of generating steam in a boiler is that combustion of fuel produces deposits inside the boiler that can slow down the flow of heat. When this happens, it takes more fuel to generate the same amount of steam. The loss of heat efficiency isn't the only problem caused by combustion deposits in a boiler. These deposits of soot and ash can cause damage within the boiler both directly and indirectly. Sometimes the deposits can grow large enough to directly cause damage when vibration causes large chunks, called clinkers, to come loose and fall down in the boiler. At other times, indirect causes of damage occur when soot and ash cause the flow of gases in the boiler to become concentrated. This concentrated flow of hot gases hastens erosion of the boiler's tubes, which can lead to tube failure. So you can see that the buildup of combustion deposits within a boiler is something we want to prevent. Now, the way these deposits can be kept to a minimum is to use soot blowers. Soot blowers are devices that use high-pressure compressed air or steam to blow deposits of soot and ash off the inside surfaces of the boiler while the boiler is operating. Now, what we're going to do in this unit is take a look at the different types of soot blowers and how they're operated and used. We'll see examples of typical soot blower maintenance problems, and we'll look at routines commonly practiced to repair and maintain soot blowers in good operating condition. There are several different types of soot blowers. Typically, there are several types installed in the same boiler, and they all make up an integrated system. There may be as many as 50 or more soot blowers used in a boiler. In just a bit, we'll take a closer look at the different types of soot blowers and how they're used. First, though, let's examine just how a basic soot blower works. Now, we said that a soot blower uses high-pressure steam or compressed air to do its job. This steam or compressed air is called the blowing medium. This picture shows the basic makeup of a soot blower. The blowing medium comes from its source under pressure through a piping system to this valve. The valve controls the flow of the blowing medium. When the valve is opened, the blowing medium is fed through the feed tube to the soot blower's blowing element. This blowing element is the only part of the soot blower that actually extends into the boiler. It has one or more nozzles that direct the blowing medium over the surfaces that have to be cleaned. A soot blower isn't operated constantly. Usually, a soot blower is operated for a few minutes every so often to blow away deposits that have accumulated. How often a soot blower is operated depends on how quickly soot and ash build up in a boiler. The type of fuel used and the firing rate are the two major factors that affect how often soot blowers are needed to clear away deposits. In some plants, this may be once every few days. In others, the soot blowers may be run several times in a single shift. Now, this example of a soot blower is just one of the three major types of soot blowers. It's a fixed soot blower. The element remains in the same position all the time. There are also rotating soot blowers and retractable soot blowers. Rotating soot blowers have elements that remain inside the boiler all the time, just like the elements of fixed soot blowers. The big difference is that the elements of rotating soot blowers rotate. They can direct the blowing medium over a much larger area than fixed soot blowers. In order to do this, they have a drive mechanism to rotate the element. This drive mechanism may be an electric or pneumatic drive, or on older systems, the drive may be a manual drive using a hand wheel or a chain sheave to turn the element. Both fixed and rotating soot blowers are typically used in cooler passages in a boiler, where the heat and the passage of combustion gases won't harm the blowing elements. In hotter areas in the boiler, such as in the furnace where combustion takes place. The temperatures are too high for metals to withstand the heat for very long. In these areas, it's necessary to use retractable soot blowers. Retractable soot blowers extend their blowing elements into the boiler only while they are being operated. The element, which is commonly called a lance tube or lance when referring to a retractable soot blower, is also cooled by the blowing medium as it operates. This further protects the element, or lance, from the extreme temperatures in the hot areas within the boiler. Retractable soot blowers can be described according to the length of their element and how far they extend into the boiler. Short tube retractable soot blowers are often called wall blowers. They go into the boiler only far enough to blow soot off the boiler's tube wall. Long tube retractable soot blowers, on the other hand, extend as much as 30 feet or even more into the boiler. These are used where short tube blowers can't cover enough of the area and where fixed or rotating stationary blowers can't be used because of the high temperatures. Most boilers use a combination of 2 or 3 types of soot blowers. Where retractable soot blowers aren't necessary, it's more economical to install less complex and less expensive fixed or rotating soot blowers. As we've said, all these soot blowers make up an integrated system used to clean the boiler while it's in operation. Not all the soot blowers are operated at once. The operation of each soot blower is coordinated in a cycle that is part of a sequence. This sequence is designed to progressively clean off deposits and pass them out of the boiler. Usually, the sequence of operation follows the path of combustion gases through the boiler. This keeps deposits that are blown free early in the path from collecting farther on. The cycle of operation of soot blowers is timed, and the control system usually has interlocks to prevent soot blowers from operating until previous blowers have finished their cycle. This makes it important for each soot blower to be kept in good operating condition. If a soot blower fails to complete its cycle, its failure can interrupt the rest of the sequence. And if this were to happen, you might be called on for some of the in-service maintenance jobs we'll be talking about a little later in this unit. So far, we've covered the 2 reasons soot blowers are used to remove deposits in a boiler. First, soot and ash buildup block the transfer of heat and reduce the boiler's efficiency. Second, deposits can cause damage to boilers both directly and indirectly. We've also looked at how a soot blower works and described the 2 types of blowing medium that are commonly used, steam and compressed air. And finally, we've seen the 3 types of soot blowers and how they fit into an integrated system on a boiler. These 3 types are fixed soot blowers, the simplest type that are economical to use where operating requirements permit, such as cooler passages in the boiler, rotating soot blowers, which are also used in cooler areas but blow larger areas clean, and retractable soot blowers, which are used where temperatures and the flow of hot gases would rapidly harm stationary elements. Before going on, stop to read section 1 of your text and work the exercises at the end of the section. Your instructor can answer any questions you might have about the material covered in this section. When we return, we'll be looking at the operation of each type of soot blower in detail, and we'll examine the types of maintenance problems that can occur in their operation. And then we'll be getting on to the real nitty-gritty of what you're going to do to keep these devices working up to snuff. In the last section, we identified the 3 basic types of soot blowers, and we looked at the differences in how and where each type is used. In this part of the unit, we'll examine more closely how each type operates and the differences and similarities between them. The most basic soot blower is the fixed soot blower. It is operated simply by opening the valve for a predetermined period. This amount of time is chosen according to certain factors such as the soot blower's location and the area it's supposed to clean. The valve may be operated electrically, by compressed air, or it may be manually controlled. The second basic type of soot blower is the rotating soot blower. This type of soot blower needs a drive mechanism to rotate the blowing element. Often a cam on the rotating element is used to trigger the opening and closing of the valve. We'll look at a way this cam arrangement typically works in just a moment when we examine short tube retractable soot blowers. In addition to the drive mechanism and valve trigger, another major difference between fixed and rotating types of soot blowers is the way the rotating element is sealed. This is done to minimize leakage of the blowing medium. Packing, similar to valve packing, is used between the element and the feed tube. This is also typical on retractable soot blowers. Fixed soot blowers have their elements firmly mounted to the feed tube, so this kind of leakage is rarely a problem. While we're talking about retractable soot blowers, we'll look more closely at the tube packing as well. Now, aside from the length of their blowing elements, or lances, the major difference between short tube and long tube retractable soot blowers is the way they're driven. The drive mechanism of a long tube retractable is virtually always powered. The drive of a short tube retractable may be power driven, or like the rotating stationary soot blower, it just may be driven by a hand wheel or a chain sheave. Also, the drive of a short tube retractable is fixed, like a rotating soot blower's drive. The drive of a long retractable travels along as the element is extended and withdrawn. Let's take a closer look at each type of drive mechanism, fixed and traveling. The fixed drive mechanism we'll use as our example here is a system used to drive a short tube retractable soot blower. This one is operated by a motor mounted at the end away from the element. A shaft from the motor's gearbox drives the main drive gear at the other end where the element goes into the boiler. On a stationary rotating soot blower, this drive gear only has to rotate the element during the operation of the soot blower. On a retractable blower, however, there has to be some way to move the element in and out. One way it can be done is to cut a pair of spiral grooves into the length of the element's tube. Two pins on the inside of the gear ride in the grooves and drive the element out and back in. The element is kept from rotating during its travel out and back in by the cam guide. A notch cut into the cam ring rides on the guide until it reaches a pawl at the end of the element's travel. This pawl releases the cam ring so the element can turn with the drive gear. After a certain number of turns, the motor drive reverses and the pawl catches the notch in the cam ring so the gear will drive the element back in. Let's see how this works in a real-life example. This is a typical short tube soot blower set up for a bench test. It's driven by an electric motor which drives through a reduction gearbox. The shaft goes to the main drive gear. Limit switches in the control box control the cycle of the soot blower. At the start of the cycle, the motor is switched on either manually, as it's done in this bench test, or automatically through the boiler's soot blower control system. As the drive gear turns, the element is driven outward. The pins that ride inside this collar act on the spiral grooves in the tube a lot like a screw that's driven into a piece of metal or wood. Notice the slot or notch cut into the cam ring and how it rides on the cam guide. When the element reaches the end of its travel, the cam is released by the pawl and starts to turn with the drive gear. The cam ring is mounted on the element, so the element turns also. As the cam starts to turn, it catches the valve trigger and opens the valve. After a number of turns, which is determined by the way the limit switches are set, the motor is reversed. When the notch in the cam ring comes around and catches the pawl again, the element stops rotating and is driven back in. The trigger is released by the cam and the valve is closed. At the inward end of its travel, another pawl releases the cam ring so the element is free to turn until the final limit switch shuts off the drive and the element comes to rest. The way the cam actuates the valve is basically the same on a stationary rotating soot blower. Only on a stationary rotating soot blower, there's no need to drive the element out and back in. The cam of a rotating or a short retractable soot blower determines how long the blowing medium blows while the element is rotating. The blowing medium can be directed over a full 360-degree circle, or if the part of the cam that the valve trigger rides on is cut a little, the arc the blowing medium follows will be shortened accordingly. The more that's cut off the cam, the shorter the blowing arc. You can also see from these examples that if the cam is turned around, the blowing arc moves around too. Changing the orientation of the cam like this is called indexing the cam. On both stationary and retractable soot blowers, there is a packing gland at the back end of the element's tube over the feed tube. The packing can be adjusted by tightening the gland follower as necessary to minimize leakage of the blowing medium. A little later on, we'll be seeing how this can be done while the soot blower is in place, and we'll also look at repacking the element too. Now, a long tube retractable soot blower is a bit different because its drive mechanism travels along with the element as it's extended and retracted. Rather than using a cam to actuate the valve, a triggering mechanism is tripped by the traveling drive as it goes out and returns. The limit switches that control the travel of the soot blower's drive and the element are external limit controls. And finally, the rotation may be driven by a chain and sprocket arrangement. The traveling drive mechanism in our example has its drive motor on the carriage. The motor drives the carriage through a chain and sprocket that turns a pinion gear. The pinion gear meshes with a rack mounted to the support rail. Rotation of the element is driven by chain from the same motor. As soon as the element travels far enough to enter the boiler, the valve trigger mechanism is tripped as the carriage goes by. As the element rotates going out, the soot blower cleans a helical path. Many long tube retractable soot blowers are set up to cycle back in with the blowing medium covering the spaces in between the helical path followed on the way out to provide more thorough cleaning. Details of how this is done can be found in the manufacturer's literature on specific soot blowers in your plant that work this way. Ordinarily, the traveling drive will trip a limit switch at the end of its outward travel, and the element will be geared to turn a quarter turn before the carriage and element begin to withdraw from the boiler. As the element is retracted, the carriage trips the valve trigger shut near the end of its travel. When the outer limit switch is tripped, the blower cycle is complete. Soot blowers are designed for precise operation under extremes of high temperatures and adverse conditions. Like any other piece of precision machinery, they must be maintained in good working order or problems will crop up. Most maintenance problems with soot blowers are common to all three types. These generally fall into 5 areas. 1, they may fail to cycle properly. 2, on rotating and retractable soot blowers, the element may bind. 3, there can be excessive leakage of the blowing medium. 4, the blowing pressure can be too low or too high. And finally, number 5, nozzles can be blocked or the end of the element may be blown off. Let's take these one at a time. First, proper cycling of a soot blower is necessary to provide for a complete cleaning job. Also, if a soot blower doesn't follow the proper blowing cycle, it can damage the boiler by causing erosion of the tubes. Failure to cycle properly can interrupt the sequence of the operation of the entire soot blower system. Things that can cause improper or incomplete cycling of a soot blower include improper adjustment of the drive and valve actuating mechanism, failure of drive power, and failure of parts in the drive mechanism. Binding of the blowing element on rotating and retractable soot blowers can also cause interruption of the blower's cycle. We'll look at binding separately, though, because it has its own causes and cures, and also because it isn't a problem with all types of soot blowers. If an element binds, it can cause rapid erosion of boiler tubes because the blowing medium is directed over a small area for a long time under extreme temperatures and pressures. Things that cause binding of the element include warping of feed tubes or elements, an accumulation of slag or ash where the element enters the boiler, over-tightening packing or not lubricating packing properly when it's installed. Excessive leakage of the blowing medium can be dangerous to anyone nearby. Leakage can occur during the blowing cycle if packing of the feed tube and element or if valve packing allows leakage. Leakage past the valve can occur when the soot blower isn't operating, if the valve doesn't seat properly, or if the stem binds. Improper blowing pressure can result in damage to the boiler or the soot blower if it's too high, because it might contribute to erosion of boiler tubes or even erosion of its own element. If it's too low, the soot blower won't do an adequate cleaning job because it can't blow away deposits strongly enough. The source of the blowing medium may be where a problem will occur, or there may be leakage somewhere else in the soot blower system. The soot blower's valve may be a problem if it's not properly adjusted. Finally, corrosion and erosion can cause the nozzles to become blocked or come loose, and the end of an element may blow off. Well, what do you do if any of these things happen? Maintenance routines on soot blowers fall into two areas. One is what can be done to a soot blower while it is in place on a fired boiler. This can include tightening packing to minimize leaking, checking for binding, and even manually driving a soot blower back to rest if it is bound up. You might have to adjust a valve for proper pressure and to assure correct operation without binding. The other area is maintenance either in the shop or out on the floor of the plant when regular maintenance is scheduled. This can include everything from basic adjustments to a complete overhaul. All of these maintenance procedures that you'll commonly have to perform will be covered in the remainder of this program. Before we continue, take time now to study Section 2 of your text. In it, you'll be able to review the operation of the three types of soot blowers and potential problems and cures for each. When you come back, we'll examine the maintenance routines that can be performed on a soot blower while it's in service on a boiler that's fired. There are going to be times when a soot blower fails to operate properly while the boiler it's on is in service. This will happen because although a soot blower is a precision piece of machinery, it operates under pretty severe conditions. In order to keep them operating the way they're designed to, it's necessary to keep them well maintained, and sometimes this means you'll have to inspect and service a soot blower while it's in place on a boiler that's fired and running. What we're going to do in this part of the program is take a look at some of these procedures for in-place inspection and service. We'll be identifying general routines you may be performing. And for specific details on the types of soot blowers you'll be working on in your plant, it's important to check the manufacturer's literature for each one. Inspection may be necessary if there is some sign a soot blower is malfunctioning, so let's look at the kinds of things that go into a good visual inspection. There are 4 things to look at. 1, observe the blowing cycle to see that the soot blower operates through the cycle freely without binding and to check the timing of the cycle. Second, you want to look for excessive leakage from the blower's tube packing. Third is to check for proper blowing pressure. And at the same time, you can look at item number 4, check for proper valve operation and look for signs of valve leakage. Each one of these items is important to seek out suspected problems. Now, how do you know when to look for problems? Well, you might not be constantly inspecting soot blowers. Although routine inspection is a good idea, it sometimes gets overlooked. These locations are often hot, dusty areas, and there may be combustion gases present too. So you won't always be spending your time up here, unless there may be some reason to suspect there might be something wrong. Plant operators observe the cycle of soot blower operation from their controls. And the information they get on boiler operation from the gauges and readouts in the control room give them a clue to what's going on. For example, the rate fuel is burned, and the temperatures in the different passages in the boiler tell them if the soot blowers might not be doing their cleaning job efficiently. And if a soot blower doesn't complete its cycle on time, or if the blowing sequence is interrupted, it's a sure thing something needs to be done. So, if there's some indication of a problem, it'll be your job to find it and then fix it. We'll take the inspection areas one by one and see what you might have to do if you find something wrong in any of these. Now, all of them overlap a certain amount. Some of them affect the others, and the presence of one problem may be a symptom of a problem elsewhere. Your text will give you further details on how these problems and symptoms can overlap one another, and your instructor can give you some practical information based on experience in your facility. In order to find anything wrong, you'll have to watch as the soot blower is operated. And when you do this, certain precautions are necessary to make sure of your safety. Keep your distance. For starters, these things operate under high pressure and often very high temperatures. Eye protection, hearing protection, and breathing protection may be necessary in some of these areas. And be sure to maintain good communication with operations people and your coworkers to make sure everyone knows what's going on. So what do you do when you find something wrong? Well, let's say that you've looked over the 4 areas of inspection as the soot blower is being operated. You've observed the blowing cycle, you've looked for leakage from packing, you've checked for proper blowing pressure, and you've looked to see if the valve is operating properly with no binding and no leakage. Well, let's take some problem areas one by one and see what their causes and cures are. We'll look at 3 common trouble spots. Of course, these may not be all you'll have to work on. For details of troubleshooting and in-service maintenance procedures on the components in your facility, you'll need to look up manufacturers' manuals and familiarize yourself with the specific soot blowers you'll be working on. In general, though, let's take an example in one area. Say you found that a soot blower isn't cycling properly. Binding is one cause of a problem with a soot blower cycle. It could be that the tube packing is too tight, and that's causing the soot blower to go through its cycle too slowly. Loosening the gland follower will cure this fairly easily. But what happens if a soot blower is bound up tight and won't move? It could be packing that's too tight, or it could be warping of the element or feed tube on a long retractable like this one. Whatever the cause, the thing you're most likely to have to do is drive the thing home manually. Some provision is made on most soot blowers to do this. It may have a drive shaft that runs the length of the support channel, so a wrench can be used to turn the drive, or some soot blowers have a hand wheel and chain to drive a soot blower that's binding. The important thing is not to shut off the blowing medium. The blowing medium cools the element, and if the element were exposed to boiler temperatures without cooling, it might fail. Leaving the blowing medium on might make the element a bit harder to withdraw, but it's got to be done. When you've got the soot blower back in its at-rest position, then you've got to figure out why it's hung up in the first place. Was it just packing that was too tight, or could it be a sagging element or feed tube? That could be the result of blowing pressure that's too low on a long tube retractable like this one. Since the blowing medium not only cools the element but also helps to keep it rigid when it's extended, if the pressure is too low, the element could bind tightly enough to freeze up the soot blower. Lubrication is an important consideration on rotating stationary soot blowers and on retractables. Lubrication points on soot blowers include lubrication of open chain and sprocket drives and grease nipples for bearings. Long retractable soot blowers have to have the front element support rollers lubricated too. Timing of the blowing cycle is another area that can require attention. On short tube retractable soot blowers and rotating stationary blowers, the timing of the blowing cycle is determined by the cam on the element. If the cam on one of these is mounted wrong, or if it is cut for the wrong blowing arc, then you'll have to determine where the problem is and try to cure it. Usually, you won't be cutting a cam to change the blowing arc while a soot blower is in place. Ordinarily, that's done most often while the component is in for shop maintenance. But it is possible to find that one was put together wrong, or that the blowing cycle for that particular blower is wrong for its location. Okay, you watch a soot blower through its cycle, and its timing is just fine. But there's a lot of leakage. Packing leaks could occur at the tube packing, like the one you're seeing here, or the valve packing could be the culprit. In either case, it's usually a pretty simple job to tighten the packing to get rid of most of the leakage. Just be careful not to overdo it, or you'll be right back up there to drive home a bound-up blower or cure a valve with a stem that's binding. Remember that there's usually a little leakage present. It seems almost impossible to get rid of it all. And one other thing, take care to protect against burns when you're working on hot equipment like this. The third common job we'll see done when a soot blower is in place is to check and correct for blowing pressure. A problem with blowing pressure could come from a number of places, and as we've seen, it can cause problems somewhere else too. If pressure's too high, The soot blower can be causing erosion of the tubes that it's supposed to be cleaning. If it's too low, the soot blower probably won't be doing an adequate cleaning job. And other problems, like the binding we talked about on long tube retractable blowers, might show up. Too high or too low a blowing pressure could be a problem somewhere else, at the source, or wherever else the pressure is regulated. Sometimes the valve that feeds the whole system may be adjusted wrong. Some systems use a restriction in the piping with an orifice of a certain size to restrict pressure. However, if the pressure is too high at the source of the blowing medium, this orifice will not control pressure as it should. Pressure to the soot blower could also be regulated by the soot blower's valve. Assuming system pressure is high enough and no leaks are present somewhere else to cause a problem, the valve on soot blowers, like these and many others, can be adjusted individually. Your shop office will have specs for each blower in use at your facility, and the manufacturer's manual for each type will give you details of how to make these adjustments. Generally, though, the adjustment can be made fairly easily. One typical arrangement has a ring on the inside that adjusts the size of the opening in the valve. You can remove a plug in the body of the valve. This exposes the inside of the body, so the source of the blowing medium must be isolated and tagged before this step is done. The plug has a pin to lock the adjusting ring in place. Once it's removed, all you have to do is turn the ring with a screwdriver from the outside. Each notch equals a certain increase or decrease in pressure, depending on which way the ring is turned. The manufacturer's manual will tell you how this adjustment is made. When you replace the plug, the ring is locked at its setting with the pin. Now, most plants will do work on soot blowers while the boiler is running. What you may be called on to do will be up to your plant's safety practices and also the type of boiler in use at your facility. But in general, the areas of in-place service we've just examined are common to jobs you may be doing yourself. In this section, we've looked at 4 items that are part of a good visual inspection. They are observing the blowing cycle, looking for leakage, checking for proper blowing pressure, and checking for proper valve operation. We've seen 3 common maintenance routines that can be performed on a soot blower while it's in place: curing problems with the blowing cycle, minimizing packing leakage, either on the element or at the valve, and correcting improper blowing pressure. We've also talked about some necessary safety precautions for this kind of work: personal protective equipment, equipment tagging, and good communications among personnel. Take time to review Section 3 of your text and make sure you have an understanding of how all this fits in with what's done at your plant. When we return, we'll be looking at shop maintenance and repair of soot blowers. In the last section of the program, we talked about the general areas of inspection and maintenance on soot blowers that are in place on a fired boiler. This part of the program is going to deal with typical maintenance routines that are performed on soot blowers during a shutdown of the boiler, when a soot blower can be removed for shop service. We'll start with the general procedures that are followed to remove a soot blower from its working location on a boiler, and we'll follow the component into the shop where it'll be torn down for inspection and overhaul. The example we'll be seeing is a short, retractable soot blower. It's the kind a couple of maintenance people can easily handle, and the routines that are followed are the same sort of general routines performed on most soot blowers. As always, in order to find out the specific details of this kind of work on the soot blowers used in your plant, you'll need to look up the manufacturer's literature on each kind you plan to service. But general practices are pretty much the same, so let's see what goes into the job. First off, in order to do a detailed teardown for inspection and overhaul, you've got to remove the soot blower from its mounting. When they get started, we'll see this done in 4 basic steps. These are, first, all the associated systems, such as the power supply to the blower drive and the source of the blowing medium, have to be tagged out as a safety precaution. Then, disconnecting the soot blower drive from its power source, loosening the blower from the mounting on the boiler wall, and separating the connection of the soot blower and the source of the blowing medium can all be done. Actually, it doesn't make much difference exactly what order you follow for the last 3 steps. Convenience, or the layout of the particular unit you're working on, may dictate a different sequence of doing this. One thing that always comes first, though, is tagging out the systems that are associated with a soot blower. Once that's done, the job is really ready to start. It's a good idea to shoot some penetrating lubricant on the nuts and studs that have to be loosened. They could be awfully hard to break loose without it. Using an appropriate wrench, each of the nuts that holds the soot blower to the boiler wall mounting can be loosened. The same goes for the nuts that hold the flange connection to the piping for the blowing medium. Now, the soot blower in our example here has a special quick disconnect plug and socket for the electrical power to the drive. Some soot blowers, like this long tube retractable type, are hardwired. That is, the wiring from the power source is connected directly to the drive. That means you might have to count on one of the plant's electricians to disconnect the power for you. When everything is loosened, it's just a matter of horsing the thing around so the blower can be pulled away from the studs on its mounting. Now, on a bigger soot blower, such as one of these long tube retractables, it'll take some careful rigging so the soot blower can be loosened from its mounts and pulled out. Once it's free, this short retractable blower can be hauled down to the shop. Shop maintenance, though, doesn't always mean a soot blower can be taken into the shop for service. It might be that a big blower such as this one has to be serviced out of the plant, just because there isn't room to bring it into the shop for maintenance. The smaller soot blower we're using for our example here can be pretty easily put up on the bench for its maintenance. The mechanics have rigged a fixture to the bench so the blower can be bolted down while it's being worked on. Here, they've already removed the protective shroud over the main drive gears. The next step is to pull off the motor drive assembly. The metal collar covers a scroll pin that holds the shaft to the output of the motor drive speed reducer. The pin is removed easily with a hammer and a drift. The motor can be loosened and pulled out, and the drive shaft is free also. In order to remove the element, the valve trigger has to be out of the way, so it's next to be removed. Cotter keys hold the pins on the pivot and the valve stem of this particular soot blower. Once the valve trigger is removed, taking off the front mount and drive gear will allow the element to be pulled. In our example, the front mount is held on by 3 nuts and bolts. The drive gear is fastened to the collar that drives the screw tube part of the element by an Allen screw. The Allen screw is locked in place by this hex nut. The hex nut is loosened and the Allen screw is backed out. The drive gear and the front mount slide over the head of the element. When the drive gear is removed, the 2 pins, called collets, that ride in the grooves in the screw tube part of the element will just drop out of the collar, and the collar will also slide off over the head of the element. On this particular soot blower, the cam may be removed from the element at this point. When the retaining bolts are removed, the cam can also be pulled off over the head of the element. The element is free to slide off the end of the feed tube. The packing gland and its flange are loose, and some packing comes out. The flange and the packing gland are next to come off the feed tube with the packing that was left behind. When the element is off, a close inspection of the feed tube will reveal any wear which might have allowed unnecessary leakage past the packing. You might satisfy yourself with a close visual inspection, maybe a careful feel for scratches or roughness. In this example, no problems are found, but the feed tube will be pulled off so the gasket that seals it can be replaced and the housing can be inspected. It's just a matter of unbolting the flange, starting with the nut that holds the bearing in place, then loosening all the rest. On this soot blower, all that's left to do to complete the teardown is to take the valve apart. Like most soot blowers of this kind, all that's needed is to compress the valve spring and slide off the keeper. If the valve packing isn't too tight, the stem and disc can be pushed on out. Now we're down to the basic parts of this soot blower. In order to inspect the individual pieces, they need to be cleaned. The element is abrasive blasted, so it can be examined for cracking, erosion, and corrosion. On parts like the valve, the seat and disc can be cleaned with a shop towel using a little non-flammable solvent. When they're cleaned, the seating of the valve can be checked. A thin, uniform coat of bluing is applied to the seating surface of the disc, and the disc is mated to the seat. Twisting the disc slightly while a little pressure is applied transfers some of the blue to the seat. After the disc is pulled back out, you can see if there are any spots where the disc doesn't seat properly. This one looks good. If the valve didn't seat properly, it might be necessary to lap the disc and seat, or the stem might be bent and the disc might not line up properly. All the old valve packing can be removed, since in this case it wasn't necessary to remove it earlier to pull the disc and stem. When the packing is out, the condition of the guide can be determined. The stem should show no sign of free play in the guide. It should move freely in and out, and it shouldn't bind. At this point, it's appropriate to clean the gasket surface on the feed tube and the housing. On a soot blower of this type, the cast housing is called a gooseneck. In some instances, depending on the age of the soot blower, it may be time now to send the casting to be X-ray tested to make sure there are no hidden cracks in the casting that could lead to failure. When inspection is complete, the soot blower is ready to go back together. Before we go any further, though, let's stop to review the general practices we've seen demonstrated so far. In order to remove the soot blower for maintenance, we saw it was necessary to tag out all the associated systems. Then the soot blower could be disconnected from its power source, from the source of the blowing medium, and it could be dismounted from its supports. In the case of larger soot blowers, we saw that rigging was needed, while smaller blowers can often be removed by hand. Once the soot blower was set up for maintenance in the shop, we saw how the disassembly, cleaning, and inspection is done on a typical short retractable blower. These general practices may differ in detail from one type of soot blower to another, but they should give you a good idea of what's necessary when you tear one down for routine maintenance. In the next part of the program, we'll look at the final steps: reassembly, reinstallation, and final testing of the soot blower. First, though, stop to study the material in your text in Section 4. Work the exercises, and when you come back, you should be well prepared for what's coming. Once the soot blower in our example was torn down, the individual parts were cleaned and inspected. The inspection revealed those parts that needed to be replaced because of wear or damage. In this instance, it was found that everything was in good condition, so the soot blower can be reassembled with just new gaskets and packing. If any parts that needed replacement, either new or rebuilt parts, would be called for. These parts would be carefully chosen to exactly replace the faulty parts with like-new pieces. After the parts and materials are laid out, and they've made sure everything necessary is there, our mechanic can start to reassemble the soot blower. Most of this is really a one-person job, just like what we've seen so far, but a helper is needed occasionally to assist. Basically, reassembly of the soot blower is just the reverse of the teardown. Since taking the valve apart was the last step of his disassembly, our worker is going to start by reassembling the valve using new packing. With the disc in place, the soot blower is bolted to the bench fixture for ease of reassembly. Holding the disc up against the seat, he installs the new packing piece by piece. Just like any good packing job, the gaps in each ring are staggered. This keeps any leakage to an absolute minimum. As soon as the last ring of the packing is in place, the gland follower is installed, just finger tight. Final tightening of the valve packing will come later, when the trigger is in place. For now, finger tight is good enough. The valve spring is replaced using a spring compressor to hold it down, while the keeper is put on to retain the spring. The keeper is slid onto the stem and the spring is released. It's held securely in place. The next step is to replace the feed tube. A new gasket is used. It's slipped onto the flange and the feed tube is held in place while the nuts are snugged by hand. In order to ensure even tightening, after the bearing and its retaining nut are installed, the nuts are tightened with a wrench in a crisscross pattern. Now we're ready for the gland follower and the element to go on. The element just slides on over the feed tube pretty easily since the packing's not in place yet. Tube packing is done after the element is in place over the feed tube. Just like with the valves packing, the gaps of each ring are staggered. The split section of pipe he's using makes it easier to stuff the packing in uniformly. The beveled end is used on each of the tapered packing rings. For the last ring, which has a flat outer surface, the squared off end is used. The cam is next, held on by 2 bolts with nuts and lock washers. He's got to be careful to index it the way it was fitted originally, or it might cause the soot blower to bind up. Then the gland follower is put into place. On the soot blower we're using for our example, a spanner wrench is used to tighten the gland follower. For now, it's just snugged down a little. He's going to have to slide the element in and out some, while some of the other parts are being reinstalled. The element's drive collar is fitted over the element, and the 2 collets are dropped into place in the collar. Now comes the main drive gear and the front mount of the soot blower. The drive gear has to slide over the collar and hold the collets in place. In order to find the tapped hole for the set screw, it's convenient to use a drift and then screw in the set screw and its lock nut. The front mount is bolted to the main casting and the upper guide rail. When this step is completed, it's time to manually drive the element back to its fully retracted position. This will get the cam out of the way so the valve trigger can be installed. The element should travel smoothly all the way. 2 pins provide the pivot for the valve trigger. They're held in with cotter keys. Cotter keys are an expendable item. Whenever a cotter key is removed in the course of maintenance, it should always be replaced with a new cotter key. Make certain that the new cotter key is of the correct size and length. Now's the time to manually run the soot blower through a complete cycle. This will make sure that the cam catches the trigger properly, and when it's driven back, that the trigger is released from the cam and the element drives smoothly back in. At this point, the tube packing can be tightened. After the gland follower has been run down tight against the packing, the worker drives the element all the way back to its fully retracted position. There should be no binding throughout the element's travel. The last step in reassembly on the bench is the reinstallation of the motor drive. The drive shaft and gear slip into place, and the motor drive output goes over the other end. A scroll pin that connects the 2 is hammered into place, and a metal collar fits over the assembly to safely retain the scroll pin. After the motor drive mechanism is in place, the power connection can be made, and the soot blower can be bench tested under power. Before he performs the bench test, the worker looks up the proper cycle for this soot blower. This way, he knows what the device is supposed to do. A simple start-stop reverse switch controls the drive. The drive's limit switches stop and reverse the drive automatically. The automatic cycle extends the element, rotates the element 2 full turns, and stops and rotates the element the other way 1 full turn before driving the element back to rest. After bench testing the soot blower under power, it's ready to go back into service. Now, all these procedures we've seen will vary somewhat from one type of soot blower to another. However, the example we've been using is a common type. It'll give you a good basis for approaching whatever type of soot blower you plan to service. An important thing to remember is to refer to the manufacturer's manual on each type of soot blower for the specific procedures that are practiced on that model. Before the soot blower is put back into place, its location on the boiler should be prepared by cleaning mounting surfaces where gaskets must seal. This particular installation has a sort of box on the boiler wall that has a purge air system to keep it clean. Air under pressure is fed into this wall box to blow dust and soot away to keep it from fouling the element where it goes into the boiler. Nonetheless, the wall box itself needs to be cleaned before the soot blower is reinstalled. Soot blower alignment is not often a problem, but sometimes there may be evidence that a soot blower is misaligned. Soot blower misalignment can cause the blowing medium to blow more strongly over part of the tubes than it should. Eventually, this will erode the tubes enough to cause them to fail. That's one clue to misalignment. Long tube retractable soot blowers that are misaligned may actually run into tubes during their travel. When a soot blower is put into place, it can be aligned by shimming at the boiler wall mounting or on external supports to square it up. When gasket surfaces are clean and new gaskets fitted, the soot blower is maneuvered into place and bolted up. The mounting on the boiler wall is snugged up first to hold the soot blower firmly in the proper position. Then the flanged connection is tightened to the piping for the blowing medium. After the soot blower is mounted firmly, it is reconnected to its source of power. Hold tags on the associated systems can then be removed, and operating personnel can run the soot blower through a final test in place. But remember, final testing must wait until the boiler is fired so the soot blower can be observed under its normal operating conditions. Then any final adjustments can be made and the soot blower is ready for some good, reliable service. Now, what we've seen in this section of the program has been a demonstration of general maintenance routines practiced on a typical soot blower. Earlier on, we examined the basic types of soot blowers, how they're similar, and how they differ. We've seen how typical soot blowers operate and what sort of things go wrong with them. All this gives you a good general understanding of the operation of soot blowers in your plant and what you need to do to maintain them in good working condition.